Hello, YouTube. Hello, Zoom. Hello, Room. We're going to start with a bit of document camera jiggery pokery. Um, based on. Do you know sometimes the lecture works better if I do the talking. Tell you what, I'll shut up until you're ready for a lecture. Better. Right. So we were mucking about actually for the last tutorial. I asked you how to get the sequence of squares out of the difference engine. And I want to show you the trick that always works, right? So there's some sequence that you're trying to get your hands on. Am I slightly... I need to zoom out a bit. So you start with the sequence that you want to generate. That's the squares in this, our example. I'll not go any further than that. And then what you do is you work the difference engine backwards, right? You take differences. So here, from 0 to 1, that's 1. From 1 to 4, that's 3. From 4 to 9, that's 5, 7, 9, and so on. Keep taking differences to all the way along, and then the differences have fallen to 0. And this is the sequence that you put into the difference engine if you want to get this sequence out. Yes?
Sorry, why is the camera like purple?
It
seems like it has a filter on it.
Your guess is as good as mine. I mean, who knows what it's been taking. Once upon a time, I managed to turn up to a lecture where all of the audiovisual equipment was completely knackered, apart from the Windows computer, which started doing an update the moment I logged in. The document camera was just producing electric multicolor psychedelic snow, and I was hosed. So I ended up saying, okay, everybody, smartphones out. Point it in the direction of this Twitter feed. I'm going to send you some pictures. And that actually worked. So there are fun and games we can have. Anyhow, here's the sequence, repeatedly taking differences at 0 gets you the way to kick off the difference engine. And your tutorial homework this week is to prove that. So the plan is, starting from any formula, you're going to figure out a way to calculate, by repeated differencing, the sequence that you feed into the difference engine to generate that formula. And it's going to take a whole bunch of, well, all the things we know. Okay, so that's a piece of machinery. Nobody ever taught you that it was this easy to kick off and calculate a series. Okay, but in this lecture, we're going to go the other way around. So let me now share. I think I'm going to share my whole screen. Okay, so here's the front page. Let's just have a quick look at the homework. So here's a little mystery for you. There's a thing you can do to the list of numbers that you use to kick off the difference engine to turn the engine for a sequence into the engine for the running totals of the sequence. And I want you to figure out what that is. It's a very tiny little tweak that you make to the starting of sequence to get the running totals instead of the thing you first thought of. And as ever, I don't expect you to just know. I expect you to try and do the proof and then figure it out. Okay. And then what happens at the end of the day, there's some stuff about some fun below. This is a nice little result. It says that you can compute P of n, the value of P at n, by starting from P of 0 and adding on n differences, which is, hopefully not a shock given what the difference is supposed to be. So, but this also is telling you that that some fun below is the notion of integration that corresponds to the forward difference operator. So it's not area under curve like your infinitesimal integration, it's running total. That's why this kind of the calculus of finite differences, as it's known, is useful if you're in the business of adding up discrete chunks of sequence. So that's where we are. And then I give you this operation here, list diffs, and you can see what happens. You've got a kind of countdown thing here. We're going to compute the first n differences. So if the countdown reaches 0, then you're done. And if the countdown still has some way to go, then you start the list with evaluating P at 0, and then you carry on, but with the difference of P. So what's going to happen is that we're going to take the 0th difference, that's to say P itself, then diff P, then diff P, and evaluate each of those in turn at 0. And that's going to give you a sequence that you can feed to the difference engine. And you get to prove that if you make the list long enough, your initial set of differences will compute exactly what the formula delivers to you. So here we're saying, yeah, here's a mechanism. Take the first however many, just plenty of differences, and that will be enough to compute the value of the formula exactly on the nose. So that's a fun thing to prove. And of course, because you know about the degree of the forward difference, that if you keep on taking differences, the degree of the formula gets lower and lower and lower until it ends up at minus infinity. And minus infinity is the degree of formulae which compute constantly 0. So you know that this list is going to end up being all zeros at the end. So for example, we're generating the sequence from the sequence of cubes from 0, 1, 8, 27, 64, and so on. And you can see that we get 0, 1, 6, 6, and then it falls to 0. So generally, the length of the list you need is one more than the degree of the formula. And that's and you can tell like what you know about degree is enough to demonstrate that. So we actually built some powerful equipment. Okay, so that's your job this week, is to turn a formula into a starting sequence for the difference engine that computes that formula. And you've got all the machinery you need to do that. This lecture, on the other hand, is going the other way around. Suppose somebody gives me the starting list with which we kick off the difference engine. Can we cook up the formula that's being computed? And, well, I wouldn't be standing here if it were not possible. Okay. So, in fact, last week's tutorial had you actually setting this up for me. So let's see. I cooked it very. Remember, we did we cooked up the sequence of the starting lists, which are k zeros and then a 1. So just a single the difference engine gets kicked off with just a single potato to start with. K zeros, then a 1. And it turns out that if you run that for n steps, you compute choose Kn. So that's to say the starting lists that just contain a single 1 generate the chooses. And it's not a coincidence that our language of formulae now includes chooses. So we proved this thing. And I've just slightly refactored the definition of 1 after zeros to use this after z's. So after z's, k is the function that shoves k zeros on the front of any list, not just the list that contains a single 1. So shoving a bunch of zeros on the front of the starting list is a useful operation. And then our 1 after zeros is shove some zeros on the front of the list, which just contains the number 1. And as before, that still computes a choose. Right. Now, the other thing that I got you to prove in last week's tutorial is this extremely useful result, which says if you add two lists together and feed them into the difference engine, you get the sum of the operations that you would have had separately. Oh, whoops, there's a typo there. That shows something. Better fix that while I remember. Right. I'll update that. Yes, there's an N missing after this thing here. Right, so that tells us something really cool, actually, because you can make any list of numbers by adding together lists that look like a bunch of zeros and a 1. Does that make sense? You know, all you have is you split, you know, if your list is 5, 6, 7, then you need 5 copies of 1 in the first position, 6 copies of 1 in the second position, and 7 copies of 1 in the third position. So you can always make any list of numbers by adding together lists that consist of a bunch of zeros, then a 1. Those lists are enough. Those lists plus adding stuff together is enough to generate all the possible starting lists. That's to say, the lists which contain a bunch of zeros and then a 1 are said to be a basis for the lists of numbers. That's to be a basis. That just means you can generate all of the things just by adding up combinations of the things in the basis.
But we use this nil, by the way, it's an infinite sequence of zeros. Basically.
Yes. Yeah. Yes.
It's kind of corresponding. Yeah.
Yes, we're essentially treating nil as an infinite sequence of zeros. Okay. So, and we know what's generated by each one. Each one generates a choose. So here's a function that just cooks up a formula from a list of numbers. And we're going to kick it off with our opening K. So if you get if we get an empty list, then we're going to give back the formula that's constantly 0. And we know that if we feed the empty list into the difference engine, it computes constantly 0, right? Okay. And then what happens is if our list begins with K, so our list begins with X, rather, we give the formula, which is choose k multiplied by x, and then we carry on with the rest of the list and with k plus 1 as our index. Of course, in general, we're going to kick this off with k being 0. So we get our first our first number in the list is going to be the constant term, and then there's going to be a multiple of choose 1, a multiple of choose 2, and so on. So the thing we need to prove to get the full generality is this thing, that if you take your starting list and put k zeros on the front of it, that's the same as evaluating the formula that you get by using your list as multipliers for chooses, starting with choose k. So that gives us a formula. Let me just, am I still on the document camera? So this actually tells us that that n squared is, I don't know if you learned this notation at school, but it's 0 times n choose 0 plus 1 times n choose 1 plus 2 times n choose 2. This is a traditional but terrible notation for the chooses that you might have learned with the binomial theorem. So this is where these results, I'm just reading these numbers off from the differences. So if you're ever wondering, sometimes people try and get you to prove these things by induction or whatever it happens to be, but you can really figure them out just by computing tables of differences like this. Okay, so this is quite a job of work, and I don't know if I'll get it all done in one lecture, but if it spills into Friday, that's fine. Let's kick it off. We have an exciting collection of variables, and we're wondering what on earth we should do induction on. But the basis of it, well, basis is the right thing. What's going on is that we're saying we're going to turn our list of numbers into the sum of a whole bunch of ones. So what's important is that we work by processing our list. And that's why I'm going to kick off with inductively. In fact, I'm going to do a bait and switch on you folks here. I have, because it will all be a lot nicer for me anyway, if I do it here. So I'm going to go inductively x's. I'm going to let Clemens off lightly today because he's got 2 other lectures to give. He's got a lot on his plate. Right. From x's. Okay. And this way, of course, I can also get nicer names. Right. Okay, so we've got 2 cases, right? In one case, the list is empty. Let's just see what we get here when we test. Right. Okay. So do we believe the base case, right? We start with a list which is completely empty, and then we make it not empty by putting a bunch of zeros in it, and then we do a whole bunch of adding up. What do you think we get when we add up a whole bunch of nothing? Right, so we do at least believe this. However, it's not going to just drop out neatly without a bit of work. Okay, so what happens next? So I'm pulling it out as a separate goal. I'm going to say given there. And this, well, now I've got to make the engine compute. I'm going to go inductively on n and from n. And again, I get a base case and a step case. I'm going to say, well, so okay. You can see that in my base case, my left-hand side is still stuck because we haven't decided whether the list is already empty or whether it's got some number of zeros shoved on the front of it. So any suggestions for what's a good move here? What would get us a bit of computation? Yes. Yeah. From K is an excellent move here, and that just does it. Okay. Meanwhile, in the step case, we get this thing. Okay, so let's not panic. Any suggestions for what's a good move? Sorry? From K might be a good move, but I think there are things worth doing first. You can see this left-hand side, we've got an engine applied to the sum of two lists. And we have a rule that allows us to split that up as the sum of two separate runs of the engine. Right? Remember that engine is a monoid map from this plus to ordinary plus. So I'm going to start with by root with this thing. Okay, and then all right. So all I'm doing, right, I mean, you spend a lot of time at high school simplifying equations and solving stuff by taking products of sums, multiplying them out, and collecting terms, right? Is this a familiar process? Multiply out, collect terms. And what was important there is that multiplying out is just using the fact that multiplication distributes over addition. That's to say, it uses the fact that multiplication is a monoid map from addition to addition. Well, all I'm doing here is the same thing, only instead of multiplying out multiplication, I'm kind of engineering out. But I'm still doing the same thing. I'm still using a distributive law to get a bunch of simpler terms that I can then manipulate. So I'm just doing the same sorts of algebra you learned at school, but with a different distributive law than the one you're used to. So I do that. And actually, it turns out that's, well, we knew that getting from the left-hand side to the middle was already justified by that distributive law. So now we're in this situation where we've got two separate engines that do a whole bunch of adding up, but we end up with zero. What's the move we need to do here? We want to know that two things add up to zero. There's only one way to make that happen. right? Is
Zero plus zero.
if they're separately zero, so the trick here is you rewrite 0 to be 0 plus 0, and ask can see that 0 plus 0 just computes down to 0. So, and then you say under plus. Okay. So now we've got one of those things just worked out already inductively. So this thing here is just this thing here equals 0 by induction hypothesis. And actually, here's my dirty trick. If you make this look enough like the goal by doing computation backwards. Oh, what happened there? Let me just get that goal again. Right. So I claim. Oh, hang on. No, I'm messing up. Actually, what should I be doing here? Do you think? Well, it's so the trouble here is that the tail is messing up, right? So actually here is the place where the suggestion from the back to do from K is a good plan. Right. Okay, and now we've got our green light here in the base case. Okay, so we're back in the room. We still got a lot of work to do. But let's look at the equation we're trying to prove. You can see that list formula is ready to do a little bit of computation. And if I say test, some computation will happen, right? We get one choose popping out after because we had one thing in the list. Okay. Any suggestions for what the next move is? On either side of the equation, do you see anything you like? I quite like this. It looks suspiciously like the right-hand side of the original goal, only for a slightly shorter list. For x's prime instead of x's. So I can now use my induction hypothesis to get rid of evaluate and the formula and just turn this into something that's talking about the way the difference engine works. So that's by root, and I should pick up the left-hand side of the goal, paste it there, change x's to x's prime, and now I need to add the rest of the context. Right? So all I've done is taken this chunk and replaced it by something we know is equal to it.
You have to replace the K.
No. Actually, I know you're right. I do. I also have to replace thank you, Clemens. That was a good save. Right. So bear in mind, this is an important aspect as ever, which is that when you do induction, the thing that you're working inductively on has to get smaller. But all the other variables can be anything you like. So here, it's just as well we're not doing induction on K, because as we work our way along the list, K keeps getting bigger. But the point is, it doesn't matter that K gets bigger, as long as the list gets shorter. So we're working our way along the list, and you can see out bubbled one term, which is some multiple of a choose. Right. So I know that middle to right is just going to be under plus. And now we have to focus on the real puzzle, which is this thing. Right. So does this begin to look plausible, right? So we know that we know something about how to make engine computer choose. We feed in K zeros and a 1. And then here, we're going to multiply by X. Okay, so fine. Let's see if we can prove something useful. I'm going to say, what happens if we prove, can we prove that choose Kn times X is equal to engine after Z's K X cons nil. Oops, what have I done? Oh, and I need an N. Right? So that's very much like the thing we did in the tutorial, except that we're multiplying choose Kn by X, and we're kicking the list off with an X instead of a 1. All we've done is multiplied that result by X. Okay. So that's what I'm going to rely on. And with that in place, I'm going to say by root after Z's K X cons nil. Well, I want to say engine. That thing. So that's the step I want to take. Right. So now I've got 2 exciting sub-goals. This one, sorry, I didn't mean to make that small. In fact, this sub-goal is going to go just straight up under plus, and I'll have to do the work elsewhere. So I still have to prove this thing. Now I have to think about this, right? Do we believe this goal that if we have K zeros, then X cons X's prime, that's the same as having K zeros, then just an X added to K plus 1 zeros with X's prime, right? If I put these 2 lists together, these 2 lists here together, I should get this whole thing here. Okay, so let's do that using our distributive law, but backwards. Like that. So now I've got a engine this equals engine that. Now I've just got a fact about lists to prove. Under engine. So, my dad used to spend the weekends under engines. So, right. Okay. So, do we at least think this claim is plausible? That these are the same lists? There's going to be K zeros, then there's an X, then there's the rest of the list. Okay. So I'm going to copy that, paste it here, and say given. Right. So that's our main proof done, but we've got a bunch of side proofs that we need to knock off. I'm going to start on this one, which is clearly stuck because we don't know what K is. Right. Uh, well, what do you know? That was one of the easier ones. That's sort of straight up. In the step case, a zero bubbles out the front. We get cancellation. The problem reduces to the induction hypothesis. That's a week 2 tutorial induction. Okay. So now we're left with the fun case. And I hope you at least believe this goal if you did last week's tutorial, because it's something you proved multiplied by X. Okay, proof's going to go the same way. In fact, I was that's silly of me. Um, right. I have to prove what? That 1 times X is X. Right. I'm actually going to pull that out separately. Right. Um, you're going to see this rare as hen's teeth move. A biroot which doesn't need any parentheses. Because all I'm going to first of all do is turn 1 times X into X. Right? And then do we believe that if we feed in just singleton X to the difference engine and we run it for n steps, we're going to add a whole bunch of nothing to that X and we'll still have an X. So let's pull this out. It is going to take an induction. We do at least have to check that, adding 0 on n times actually does it. Inductively n from n. Oh, even easier. Right. So now that's given. Right. Now here, this is a job for from n. And I get a step case. Okay. And now that choose is ready to compute. So let's say test. Right. So what are we going to do? We're going to do what we always do. We're going to do several different flavors of multiplying out. Right? You can see here I've got a multiplication outside a sum. And, you know, I really want to get times x strapped to each of the chooses. You know, we've got an induction hypothesis that talks about choose something times x. If I can get my times x nearer my chooses, then I'll have some chance of using my induction hypothesis. So that's a start. Will I get this done by the end of the lecture? Okay. So that's just straight up distributivity. What's my other move? I think I'm going to use the fact that engine distributes through list plus. And that's going to get me things that look like the way I want them to look. So that's going to be this thing with M here, ordinary plus, engine. And do you know what? That is after Z's successor of J. Have I got the right number of parentheses? No, I've messed that up somewhere. Got too many here. That looks about right. And now I think it might just line up nicely. Hold on. With 5 minutes to go. So, goodness me. I mean, clearly all a bit fast. Obviously, all of this code will end up on the lecture page, and you have the opportunity to replay it. But what we've got here is a way to figure out a formula that comes from a bunch of differences. And if you've got, and you can get your differences just by calculation. So do you remember once upon a time, if you were taught induction at school, you may have been made to show that if you add up the numbers from 1 to n, you get half n times n plus 1. That ring a bell? It might do, it might not. But you were just given this formula and asked to prove it, but no one told you how you would figure out the formula. Well, let's do it. Right. I'm going to, instead of adding up the numbers from 1 to n, I'm going to add up the numbers strictly less than n, because that's just the way of managing it with better taste. So if you add up the numbers less than 0, you're not adding up any numbers. So that's 0. If you add up the numbers less than 1, then you're adding up one number, but that number is 0. So you've still got 0. If you add up the numbers less than 2, that's 1. If you add up the numbers less than 3, that's 0 plus 1 plus 2, that's 3. And then we know we get 6 and 10 and so on, the triangle numbers. Okay? So now what do? We figure out how we would kick off the difference engine to generate this sequence by taking differences. These are indeed the numbers we were adding up a moment ago. And then difference of 1. And then we've stabilized at 0. So this is our sequence that we kick off the difference engine with. And we know, we've just seen how to turn that into a formula. This is 1 times x choose 2. So the sum for I less than n of I is exactly n choose 2. That's half n times n minus 1. So that's because this is strictly less than n. Okay, so that's where the formula comes from. And I can manufacture it mechanically just by computing the differences and then using the result we just proved to generate a formula by using these differences as multipliers for chooses. So no mystery, no magic. You can turn a series into a formula that computes the series by repeatedly taking differences and using those differences as multipliers for chooses. It's just an incredibly handy bit of mathematics that weirdly nobody teaches young people. I mean, Isaac Newton figured this out in the 17th century and seems we've forgotten it in the meantime. Anyway, I'm shocked that that actually made it out the door. I didn't even know at 6:30 this morning that I was going to be able to prove this. And here we are with a shocking result at 10 to 10. So that's kind of cool. So your mission is to fill in the blank that says that if we compute repeatedly differencing, that's the right way to kick off the difference engine. But we've put together something pretty cool. We're at the stage of time where we're just winding up and collecting all the bits together and presenting a result tied up neatly with ribbon. So have a lovely day, have a great rest of the week, and I will say cheerio to YouTube and Zoom, if only I can find the button.